Yeah. So, today we will discuss in this lecture the derivative of the function at a point as well as on the interval, and also the mean value theorem, differentiability, differentiable. Differentiability or derivative of the function, derivative of the function f x of real variables. Let f x be a real variate. Let f be a real valued function defined over the interval say a b, over the closed interval say a b. Then the function f x is said to be differentiable at a point say x naught belonging to the interval a b, if the limit of this function f t minus f x naught divided by t minus x naught, limit t tends to x naught, if this limit exists and finite, of course, finite. In case infinite, we say if the limit is infinite derivative, then the differentiability we can also discuss the case of infinity later on only. Okay. So, let us say just exist, then it is denoted by f prime x naught, or we also say d over dx f x at a point x equal to x naught. That is also a notation to use the derivative at this point. So, now, here if the point is coinciding with a or b, then in that case we have a different concept. Now, when we say the limit of this exists, that is 1, if this limit exists means the existence of 1 means that both the limit, both left hand and right hand limit must exist at a point x naught which is in the open interval a b, and both are equal. Then we say the derivative of the function exists. At the corner point at x naught is equal to a, we consider only the right hand limit, that is we consider the limit t tends to x naught, say x naught is a. So, here t tends to a plus f of t minus f of a over t minus a. So, this is an interval a b. We will look only this side, the point which are approaching to a from the right hand side of a. So, this point t a plus. So, right hand limit of this, if it exists, then we say the derivative of the function at a point a. Similarly, the derivative at the point b, that is at the end points, this is the end point interval, means limit t tends to b minus f of t minus f of b divided by say t minus b. Okay, when b tends to t tends to b minus. So, if this limit we are taking the point, this is b and we are approaching towards this side left of the b. All the points are taken in consideration which are left to b, and at this point we are taking the image of this when t tends to b minus. Then we say the function has a limit at the point b. So, if the function f is continuous, if the function f is continuous at every point of the closed interval a b, including at the end points, at end points, then we say the function f x is differentiable over the closed interval a b. Similarly, we say the function f, if f is differentiable, not it is differentiable at every point of the interval including end points, then similarly a function f is said to be differentiable over the open interval a b if it is differentiable at each point, at every point of the interval a b, like this. So, we can extend this definition to that side. Now, using this definition, one can easily show that if f x equal to 1, f x equal to x, the derivative will be 0. If f x equal to x, then the derivative of this function will be 1. In general, if f x is x to the power n, the derivative will be equal to n x n minus 1, which can be used, which can be proved directly with the help of this results. So, all the polynomials functions, all polynomials are differentiable functions, are differentiable function for each x belongs to R. Then polynomial p x, they are all differentiable function. Then trigonometric functions, like sin x, cosine x, tan x, these are all differentiable functions in the their domain, differentiable in their domains. Okay, like this. So, these are all examples which is just results which we know in the calculus, the differentiability of a various functions and formula is followed. So, we are not going in detail for that, but this. Now, interesting result is that every differentiable function will be a continuous function, that is. So, let f be defined on the closed interval a b, on the closed interval a b, if f is differentiable at a point say x belonging to the interval a b, then f is continuous, at x. Okay. The proof is just simple. Okay. We want the continuity. So, let us take the point t which goes to x. Okay. So, take f of t minus f of x. This can be written as f of t minus f of x over t minus x into t minus x, where the t is different from x. So, obviously, this is well defined. Now, as limit t tends 2 goes to x. This gives the derivative f prime x by definition, and this part will give the 0. So, total will be 0. Therefore, limit of f t when t tends to x either from the left hand side or from the right hand side, if this limit exists means it both will be equal. So, it will always give the derivative, and this will go to 0 whether we approach t from the t to x from the left or right. So, this will always be when t tends to x, the f t will be equal to f x. That is, the limit exists and equal to the value of the function at the point where the limit is required. This implies the function f is continuous at the point x. Okay. So, we have discussed this thing, the differentiability, and for the differentiability just we need only the functions to be well defined in this. And so, what is required now? If you look that this example shows or this result shows that continuity is a necessary condition for a function to be differentiable, because every differentiable function we are getting continuous. Okay. So, continuity comes automatically when the function is differentiable. So, it is a necessary condition for the functions to be differentiable, is it not? Then we say the converse of this. So, as a remark or note, the continuity of the function f x is necessary condition for a function f to be differentiable over the a b or at any point, or at any point. Any point x belongs to a b. However, this condition, continuity of the function f is not a sufficient condition. For a function f to be differentiable. For example, if we look the function f x which is equal to mod x, the function, the curve of this function is like this: x is 0, it is 0. When x is positive, then it y equal to x. When x is negative, y equal to minus a. So, we are getting again this one. So, this is the graph for mod x. Now, it is very smooth curve, it is a continuous curve. In fact, the function f x is continuous everywhere, say everywhere. I just take the interval for my convenience is 1 to 1, including at the point x equal to 0. The reason is because suppose I want to test at the point 0, what is the limit of the function f x when x approaches to 0 from positive side? The limit of this is nothing but what? F x is x. So, it is x, f x is s, and then limit x tends to 0 from positive side. This is the same as limit h tends to 0, 0 plus h, which is 0. And if you look the limit of this function f x when x tends to 0 from the negative side, then we say it is the limit x tends to 0, because all negative. So, it is x is minus, mod of x is minus x. Okay. So, this is minus x, x tends to 0, that is x equal to x minus h. So, we can write limit x minus h, a negative quantity, and then h tends to 0, x is 0. So, we get again it is 0, and the value of the function is equal to f 0. So, limit exists, limit of the function f x when x tends to 0 is 0, which is the same as f of 0. So, function is a continuous function at 0. So function f x, which is mod x, is continuous at x equal to 0, but it is not differentiable, but it is not differentiable at x equal to 0, because the reason is, if we find the limit of this function f x minus f 0 divided by x minus 0 as x tends to 0 from the positive side, what we get? Limit f x when a positive side is mod x, mod x means is simply x only. So, it is nothing but the x only, because it is positive, minus 0 and then divide by x, and x tends to 0 plus. So, this is 0 plus means when x is positive, mod x equal to x. So, limit comes out to be 1. When x tends to 0 minus, the f x minus f 0 over x minus 0, this is the same as x minus. F x equal to mod x, when x is negative. So, it is minus x minus 0 divided by x when x tends to 0, but that comes out to be minus 1. So, what you are getting is the right hand limit comes out to be plus 1, left hand limit comes out to be minus 1. Therefore, limit of this function f x when x tends to 0 does not exist. Sorry, f x f minus f 0 over x minus 0, this does not exist. That is, the derivative of the function at a point 0 does not exist. So, function is not differentiable. It means the next continuity is no longer the sufficient condition. Okay? Just by looking the function is continuous, you cannot say the function must be a differentiable function. No, but it is a necessary. That is, if a function is not continuous, we cannot talk about the differentiability of the function. Function cannot be a differentiable if it is not at all continuous there. So, that is a very important result for that. Then, just like a limit case, we have proved that in case of the limit, if all continuity, if f and g are continuous, the addition of the two function is also continuous, subtraction is continuous, multiplication of the two continuous functions is continuous, like this. So, similar results here also hold for differentiable functions. The results are in the form. Let suppose f and g are defined. F and g are defined on the interval say a b, closed interval a b, and are differentiable at each point x belongs to a b. Then f plus g, f minus g, f g and f y g are differentiable at x, and the values of the derivative this x is the same as f prime x plus g prime x, b f g derivative at a point x is the derivative of the first function f x multiplied by the second. This is the product of the derivative of two functions. So, derivative of the first function multiplied by second plus the first function into the derivative of the second. Similarly, when we say the derivative of the ratio of the two differentiable function at a point x, x is the denominator g x into the derivative of the numerator f prime x minus numerator into the derivative of the denominator divided by the square of the denominator, provided the function g is not 0 in at any point where the differentiability is tested in this interval. So, let us see the proof is just one or two proof. Let us see. A is obvious, that follows by definition. Right definition we can just use it. The part B, you just construct, let h equal to f g. Suppose this function, then consider this difference h t minus h x. Now, this can be written as f t, then g t minus f x g x, and then plus g x into f t minus f x. Now, you just see that f t g x and f t g x is subtracted. So, subtracted and added. So, this will be 0 here, okay, and rest will be, we are just taking h t is means f t g x, here h of t means f of t g of t. So, h of x means f of x g of a, where this means like, okay. So, just is balance. Now, divide by, as t is different from x. So, divide by t minus x. So, when you divide by t minus x, okay, what you are getting is f t g t minus g x over t minus x plus g x f of t minus f of x divided by t minus x, and then let t tends to x, let t tends to x. Now, what is the right hand side? The right hand side is when t tends to x, f of t will go to f of x, because f is already giving to be, f is giving to be a differentiable function. So, it must be continuous at the point x. So, when you take the t, x is here and this is the interval. So, either t is this side or maybe t is this side, function is continuous. So, f of t, limit of f of t will be f of x. So, this will be, and this ratio g t minus g x over t, it is also given the function g is differentiable function at any point. So, at a arbitrary point x, it is differentiable. So, this limit will be equal to g prime x, because t tends to x, and this is g x and this will be f prime x, and this will give the derivative of the function at a point x. So, this proves the B part. C portion, to prove the C, let us consider h to be f by g, where h of t means f t by g t. This is the meaning. Okay. Now, consider this h t minus h x divided by t minus x, just and that manipulate the term. So, what you are getting is h t means g t and g x will come. So, it is basically f t by g t minus f x by g x. So, when you take the LCM, then you are getting g t g x outside, and inside we are getting h g x g x into f t minus f x, f t minus f x, and this t minus x take it here, then plus minus f x into g t minus g x divided by t minus x. Now, you see t minus x suppose outside, then all these things are adjusted. You can just say this g x f x and f x g x both get cancelled, and rest of the things will come from here. So, as t goes to x, as t tends to x, this one will give as g x. So, g x square, and this one will give g x, and then this is the limit of the f at the point x, derivative of f at the point x, because this limit ratio of this limit give the derivative minus f x into the derivative of g at a point x, and this will give the derivative of the function h at, means derivative of by g. So, that result follows. Okay. So, these are all fundamental things, and we can use it for getting the derivative of various type of functions. Now, for the composite functions also the similar results hold as we have in case of continuity. Just like a function f is continuous at certain point, and g is also continuous at the point f of p, where the image of point where the function is continuous, then f composition g is continuous at a. So, just like a continuity, the same result follows for differentiability. So, suppose f is continuous on the closed interval a b, and let f prime x exist at some point say x of a b belongs to a b. G is defined on an interval I which contains the range of f, and G is differentiable at the point f x, Okay. Now, if h of t equal to g of f t for t lying between this a to b, then g h is differentiable at x, and the derivative of this is equal to the derivative of g with respect to this f x, and then f with respect to x. Now, remember here I will just explain. Here we say note, when we say g dash of f x, it means we are differentiating this g with respect to f, and then f with respect to x, So, and f dash x is df over dx. So, when we are saying the h dash x, it means we want to differentiate this composite function g of f x. This composite function we want to differentiate with respect to x. So, since it is a composite function, g is a function of f. So, first we have to differentiate with respect to that composite function, and that composite function with respect to x. That will be the idea for it. Okay. So, that is the value for this. Okay. So, we get suppose for example, let me see just one thing. Suppose for example, I say the h function h of x equal to cosine of x square. Say suppose I take this, then f x is x square, g is cosine function. So, when you differentiate this h with respect to x, you will define cos with as if x square is t, a function of t, then cos of as a function t is the sine minus sine, derivative of cos is minus sine x square, and then x square will be differentiated with respect to x. So, that will give 2x. So, that is the composition. Okay. So, this is all. Now, let us see the proof of it. Okay. Let y is equal to f x, y is equal to f x. Okay. Now, since function f x is continuous as well as differentiable, it is given f is continuous on a and derivative exists at this point. So, by definition of the differentiability of the function f x, we can say, so by the definition of the derivatives of the derivative, we have f t minus f x, this is equal to t minus x into f prime x plus u t, where u t tends to 0 as t tends to x, u t tends to 0 as tends to 0, and t belongs to a b. Let us see what is the meaning of this. When we say the function is differentiable, that is, the meaning of this is the function f prime x exists. It means it is the limit of this f of t minus f of x, f of t minus f of x divided by t minus x when t tends to x, is it not? So, when t is approaching to x, then this ratio, the limit of this ratio exists and we are denoting by f prime x. It means the difference between this ratio and f prime is very, very small when t is sufficiently close to x, or in other words, if you say that if I multiply this t minus x to this, or we can say that this ratio f of t, sorry, this one f of t minus of this over t minus x is this. So, if I remove the epsilon t minus x, then this is equivalent to the derivative of the function at a point x plus some number, say u t. I am taking u t, it may be epsilon, and this u has a property, it goes to 0 as soon as t approaches to x. So, when you take the t approach to x, if this part is tending to 0, so this will coincide with the limit of function, will coincide with the derivative. Okay. So, the same thing I am rewriting in this way, that f of t minus f x is t minus x times this thing. Okay. So, this is what we get. Now, similar thing we can write it for our function g. Now, g function is defined over an interval I in which the range of f lies. So, similarly, so let it be equation 1, and similarly for g t, g of s minus say g of y, because a function g is continuous at the f x, f is continuous, f is differentiable at x. So, g f x is differentiable, g is differentiable at f x. So, y is equal to f x, I am writing the g of f x here, which is s minus y into g prime of y plus a term v s, and the v s tends to 0, where the v s goes to 0 as s tends to y, s tends to y, okay, and s belongs to the interval I in which the function f, the range of the f lies. Means this is our, say here. So, the function f is defined over this domain, this is the domain. So, x is here, we are getting f x here. The function g is defined over an interval I am in place of integer I am just writing this I, where the range of this f is contained. So, when you take the g, then g is defined as g of f x, is it not? This defined, and function f is differentiable at x and g is also differentiable at f x. So, we can write it this as this form. Okay. That is what gets to it. So, this can be where t belongs to, where t is this. So, let it be equation 2. Okay. Now, suppose in this now we wanted the function h t, this is we wanted to show that h function, which is a composite function h of t, which is g of f t, is differentiable at x. This we wanted. So, write down the relation h t minus h x. So, consider h t minus h x. Okay. Now, h t minus h x means h is this function g of f t. So, we can write this as g of f t, this is h, minus h x means h t and h x means g of f x, this thing. Okay. Now, replace this s by f t, because s is a point in the interval I. T f is a function defined over the domain and t is a point in the interval a b. Okay. So, replace s by f t. So, when you replace s by f t, what you are getting is this g of f t minus this. Now, let us see g of this, if I replace this in equation 2. So, if we replace, let this be taken in equation 2. So, from the equation 2, what we get? 2 is g s minus g y, is it not? So, g s minus g y, g of f t minus g y, g of y means g of f x. This is our and which is nothing but this part h t minus f x, which is the same as h t minus h x. So, if I replace this s by f t, then from here we are getting this one, but the right hand side of this gives you s minus y. So, s will be equal to what? G of f t. So, this is equal to g of f t minus g of f x, that is the same thing which I have written. Okay. So, now apply this here, f t minus a, f is continuous differentiable. So, we can use this thing now. So, when you use this thing, then this becomes g is differentiable. So, it is f t minus f x into g prime at some point by where it is continuous plus v s. Okay. That is what we get in. Use this one condition. Then similarly, for this g of f x. So, when you write this thing, the g of this difference is this one s minus by s is our f t, by is equal to f x, g prime by plus b s. This one we are getting, this get it from 2. Okay. Now, apply the first, use first f t minus f x is this. So, use first. So, it will be equal to t minus x, f t minus f is t minus x into f prime x plus u t. This is our f t minus f x. We want this value I am replacing by this, and here this remains as it is, say g prime by plus V s, that is as it is it not V s. Okay. Now, let us take this now. So, if t is not equal to x, then we divide by t minus x. So, when you divide by t minus x, you are getting h t minus h x over t minus x is nothing but what? F prime x plus u t into g prime by plus V s. Okay. Now, this will be equal to what? Taking the limit as t tends to x. So, when you go to the limit as t tends to x, the right hand side if I look, as t tends to a, u is tending to 0 because of this condition is already given, f is differentiable at x. So, u t will go to 0 as t tends. So, this part will go to 0, similarly, this part will go to 0, the right hand side will give f prime x g prime by, and the left hand side is nothing but the derivative of the function at a point x. So, this implies that the derivative of this composite function g of f x with respect to x is the derivative of g with respect to f x, then derivative of f x with respect to x. That is what it shows. So, this proves the result. Okay. So, that is what. So, this is composite function which is very much helpful in getting the product. Okay. Now, let us take few examples where the differentiability is there. Okay. Suppose I take the function f x equal to x square sin 1 by x when x is not equal to 0 and 0 when x is equal to 0. Okay. Now, when x is not equal to 0, what you are getting is the function is defined in this fashion. Now, x square is continuous function, it is also differentiable function, sin is continuous and differentiable so far x is not equal to 0. So, we can directly apply the formula, and when we take x is not equal to 0, when x is not equal to 0, you can directly apply the formula product of the two function, and product of the two function will give the derivative of the first 2x sin 1 by x, and then the second function x square and the derivative of this is cos 1 by x into minus 1 by x square, because this is a composite function now. Derivative of sin as a function 1 by x is cos 1 by x, but 1 by x derivative is minus 1 by x square. So, it is a composite function. So, this holds when x is not equal to 0, that is the derivative of the function comes out to be 2x sin 1 by x minus cos of 1 by x for x which is different from 0. Okay. But when x is 0, what happens? The derivative of the function we have to compute it. Why? Because at the point x is 0, when you are looking for the derivative, then the value at this point apply the value which are different from x 0 is given by this form. So, find the derivative of this function at the 0 by using the definition, that is limit of this f x minus f 0 over x minus 0 x tends to 0. Okay. And that comes out to be what? F x is x square sin 1 by x minus 0 divided by x when x tends to 0. So, that is equal to basically limit of this x tends to 0 x sin 1 by x. Now, if we look that term x sin 1 by x is always be dominated by mod x, So, basically when you are taking the mod of this, then this is mod of this which is less than equal to mod of x limit x tends to 0, and this limit will always comes out to be 0. Okay. This limit comes out to be 0. Therefore, the limit of this exists and the derivative at the point 0 will be 0. Okay. But what about the equation? Let it be this equation 3, this is 4. The function is differentiable. So, conclusion is the function f x defined by, say, here star, defined by star, is differentiable throughout x belongs to R, including x is 0, but the derivative of the function f x, if you look, the derivative is not continuous at x equal to 0. Why? Because when you take the derivative is involving cosine of 1 by x. So, when you take the limit as x tends to 0, the limit does not exist, because limit of the cos 1 by x as x tends to 0 does not exist, which is available in 3, because use 3. Okay? Then we are getting. So, when the function is differentiable, you cannot say that derived function remains continuous. It may not be continuous. If it is continuous, then there is a possibility of going further, is it not? But if it is not continuous, we cannot talk about the derivative. So, in this case, we cannot talk about the differentiability second derivative of the function at a point 0. Okay? If we look, the f x is similarly x sin 1 by x, we will see in a similar way the limit does not exist. Similarly, example 2, if we take the function f x, x sin 1 by x, x is not equal to 0 and 0, then function is continuous. F is continuous because at 0 and also for all x belongs to R. In fact, continuity follows, but not differentiable at x equal to 0. It is difference at rest of the point, rest it is differentiable, because when you take the derivative of x for x is different from 0, you can just apply the formula. First function x, derivative of this is cos 1 by x into minus 1 by x square, then plus sin 1 by x. So, the derivative will come out to be minus cosine 1 by x divided by 1 by x and then plus sin 1 by x, when x is different from 0. But when you consider the derivative at a point 0, then as per the limit f x minus f 0 divided by x minus 0, x tends to 0. This comes out to be sin 1 by x minus 0 by x, x sin 1 by x minus 0, limit x tends to 0, which turns out to be limit of 1 by x as x tends to 0, which does not exist. So, this function is third continuous function, but is not differentiable at the point 0. It is differentiable at rest of the point, but not at the point 0. Okay? So, we can get. Now, there are certain mean value theorems which we will make use for that. So, before that, let me see the definition again for the maxima minima, local maxima, local minima. This is already we discussed local maxima or local minima. Let f be a real function defined on a metric space, x t. We say then f has a local maxima or local maximum at a point P belongs to capital X if there exists a delta greater than 0 such that f of q is less than or equal to f of p for all for all q belongs to x satisfies the condition with the condition that distance from p, distance of q and p is less than delta. Distance of this is less than delta. So, this is it means what is the local minimum? Suppose this is our x t, a metric space, and p is a point. We say the function attains a local maximum at this point if there exists some positive number delta and a neighborhood around the point p such that if we pick up any arbitrary point q here, then value of the function at this point q should remain less than or equal to p, then we say the function attains the local maximum at this point. Okay. Just for example, if we take the function say f x equal to say suppose this function I will say x when lying between 0 less than or equal to x less than half and say equal to 1 minus x when x is say half and say 1 okay, less than 1. So, what this function is? If we look the function f x equal to x between 0 and half, the function is defined like this. At the point half, the function is again half. So, it attains the value here and then 1 it is again 0. Okay. Now, if I look the point half, what is the character of the point half? If we take any neighborhood around this point with a positive delta, say half minus delta, half plus delta, this interval if I choose, then the value of this of any point here in this neighborhood will be somewhere here or somewhere here, which is less than the value at the point half. This is the value of the function at a point half. So, we say half is a point corresponding to a local maxima of this function f. The same definition continue for a local minima. Local minimum we say a function f has a local minima at a point say p belongs to x if there exists a delta greater than 0 such that f of q is greater than or equal to f of p for all q belongs to x with the condition that distance from q and p is less than delta. So, this is the local minima for this point. Okay. Now, we will continue with the main value theorem next time. This all. Thank you.